Welcome to lecture number 20 for ECE476 Advanced Embedded Systems. In this lecture, we're going to look at text files and measuring the energy in a battery. Now, the Pi Pico has 264K of on-chip RAM. That allows you to create text files which control how the Pi Pico operates, let you write to text files, saving your data. And this lecture is going to cover how to open and close text files, how to read from text files, string commands and parsing, so you can sit there and pull out columns of data, reading your text file to play a tune, writing to text files, and measuring the energy in a rechargeable battery. So that's where we're heading. So let's start out. To open and close text files, the Python command to do that is an open command. So if I say pick any name you like file, I'll open, this is the name of the file, and the access mode. Now, the access mode can be R. That's the default mode, meaning read. The file has to exist already. If it doesn't, you get an error message. You can do A, append. If the file does not exist, it creates a new file. If it does exist, the following data that you write to it goes at the end of the file. There is W, which will create a new file. If the file already exists, it will clear it and start over. And X just creates a new file. Now you can also specify whether it's a text or binary file. For example, we're going to be using text files, so you can read them with Notepad. A binary file would be like an image, a JPEG. Once you're done with the file, you should close it. That's the file close. So that's kind of the idea behind files. And there's a couple different ways to read a file. If I want to read a text file, I can read so many characters. Like if F is the name of the file, read of 5 will read in the next 5 characters. Read line reads in the whole line, looking for the character return line feed. Read lines, plural, reads in the whole file and stores it in an array. And read reads the whole thing into a text string. So, for example, let's go to the Pi Pico actually. Go to the Pi Pico and do File, Open, and go to the Raspberry Pi. Suppose there's this file called README. This is what's contained in that file. If I want to read it, I would first have to open the file. I think I should do that over here. If I say F equals open, I want to do the default RT. That opened up the file. If I read in the entire file, that's what I have. I could just read in a single line. This restarts it. If I just read in 5 characters, that's the first 5 characters in the file, I can read in the whole line. That reads in the whole line, stops at the character return line feed. If I do that as read lines, data is now a string array. Here's the first string, second string, third string. I can say what is the first line of data, the second line of data, the third line of data. Note that files are stored as a text string. /R is a character return. So at the end of the line, if I do like date of 0, I've got a /R/n. That's a character return line feed. That's typically how strings are terminated. You can read that line by line if you want. This would be going through a for loop, read lines, reads it line by line, printing each line one by one. So that's kind of how you read a text file. Now, if your text file contains data, like the Arctic sea ice, if you go to many places on the web, there's lots of data. If you go to ECE111, that's one of the courses taught in ECE. This has got a bunch of different data sets you could look at, like CO2 levels versus year. Here's the year, here's the CO2 level. Here is temperature deviation, global temperature changes versus year. Arctic sea ice versus year. Suppose you have one of those data sets and you'd like to plot it. Well, typically the data to plot is in columns separated by a comma, a space, or a tab. What I'd like to do is when I read this in, I'll read it in as a string. Can I pull out the different columns? Well, that's using some of the string commands in Python. With string commands, I can do read lines that reads in a full line of data, including the spaces. If I do strip, strip pulls out the spaces at the beginning and end of the string. Replace will replace the commas, tabs, double spaces with a single space. That just gives you consistency in the data, so there's just a data, single space, data, single space. I can then find the columns of data. I'm going to look for a space. When I find it, that tells me that the first string goes from 0 to where the space is. The second string then starts at space plus 1, goes to the next space. So what that's, by looking for the spaces, I can tell you how many different columns you have. And by appending it, I'll wind up with an array of data. Each column is your string. When you read data, this is a string. To convert it to a number, I need to do float or integer, convert the string to a number. That's what float does. If I then want to plot the text file, that is a function in the LCD library. I'll just read in the data. So here I'm going to open up sea ice, read in all the data in an array. Data of 0 is the first line, second line, third line. Pull out the different columns, and then plot column 0 versus column 1 and column 2. So for example, plotting first column versus the second column. If I run this file, it's going to ask for the name of the file. Here's the data, and then plotting column 0 versus column 1. That's what it looks like. I'm going to plot column 0 versus column 2. That's the maximized extent. Okay, so I can plot data, read data, do stuff like that. Second thing you can do with text files, I can use that to control my program. So we looked at before how to play a tune like Super Mario Brothers. Well, if I store that tune in a file, I can sit there and play the file. Change the name of the file, I'll play a different tune. So what this does is this is the note E, the octave, and the number of beats, the 16th of a beat. 0 means play no sound. I want to play that file. So to do that, I need to come up with a parse routine. What that one does is if I have something like E4, I need to pull out this string, and then the number of beats, like 3, pull out that string. So that's what this parse does. What it does is it first clears out the spaces at the beginning and the end, replaces commas and tabs with a space, replaces double spaces with a single space, and then finds that space, this guy right here. The note will be the first field. The second field is the duration. Return that. Now, using that, what I can do is open the name of the file I want to play, read in the data, and then for the whole data set, pull out each note one by one. So here's the first note. I want to play note E4 for 2 beats, E4 for 2 beats, E4 for 4 beats, and so on. That's the first step. Second step, I want to convert this to a frequency in hertz. Now, if you go to Wikipedia, the 0th octave has this frequency. Each octave after that is scaled by 2 to the n. So I'm just going to do a bunch of if statements. If the field is C at 16.35, C sharp 17.32, D 18.35, and so on, scaled by 2 to the octave, that gives you the hertz that you want to play. Now, anytime you write a program, you want to test it, so let's try that. If I have the note A3, it is 220 hertz. That's correct. If it's D4, 293.6 hertz. Also correct. G5 sharp, 830.72 hertz. Okay, so now that that works, I can play a tune. So I'm going to reuse the play command that we had before. I'm going to play a certain frequency for so many sixteenths of a note. Should be sixteenths. What that does is, if the hertz is not 0, play that note, otherwise be silent. For this duration, minus 50, so there's a little pause between notes. And then at the end, sleep for 50 milliseconds. Now, using that, I can spin through the file, and for each note, I'll pull off the frequency, the duration, print it, and play it. So here's what that sounds like. So here's the file I want to play, Super Mario Brothers. And to play it, and over here, this is the note, this is the frequency in hertz, here's the number of beats. And by changing the text file, I can change the tune. So that's some of the uses of text files. I can save data for plotting. I can save data to control the program, like playing a tune. Next thing to look at is writing to a text file. Now you can also write to text files. What that does for you is you can save your data for later analysis, such as what's the voltage of a discharging battery. When you write to a text file, the options you can use are A and W. A will append to the old file, so you don't lose your old data. W clears out the old file and creates and starts over. When I write to a text file, if I want to throw in a carriage return, I need to throw in a /n. That terminates the line. For example, if I just say for 0 through 6, I want to write the string I, followed by an X, the string I, followed by a carriage return. What I get is 0x0, 1x1, 2x2, and over here, this is the carriage return showing up as the next line. And again, anytime you open a file, you need to close it at the end. So that's basically how to write to a text file. To open a file from Thonny, just go to, I'll show you here. I'm going to do File, Open. In this case, I want to read it from the Raspberry Pi. I could do something like, here's my 9-volt battery. That's the text file that I wrote to. So with that, let's have some fun. Let's just read the analog inputs and save it every 100 milliseconds. So what I can do is read the analog input, 0, 1, 2, convert to volts for sample size of 10. I'm going to read the voltage on each A to D, write I in the voltage, followed by a carriage return, wait 10 milliseconds or 100 milliseconds and repeat 10 times, then close the file. If I do that, when I then open the file, what I see is the first one is I, sample number V0, V1, V2. Okay, so now that I can write to a data file, let's do something with it. Let's measure the energy in a AA battery. Now to do that, what I'm going to do is take a AA battery, rechargeable AA, somewhere around here. One of these I got off Amazon. I want to find out how much energy is in it, so I'm going to discharge it across a 10 ohm resistor. To size the resistor, the power is V squared over R. So 1.5 volts over 10 ohms is 225 millivolts, or 225 milliwatts. This has to be at least a quarter watt resistor. If it's a 9 volt battery and I use a 47 ohm resistor, that's 9 squared over 47, about 2 watts. Got to make sure that's a 2 watt resistor, otherwise it's going to get really hot and burn out. Also, the Pi Pico can only handle 3 volts, 3.3 volts, so the 1.5 volt battery is not a problem. The 9 volt battery is too much voltage, so if I add a divide by 3 circuit, that keeps this in the range of 0 to 3.3 volts. That's the hardware. In terms of how long I have to run the experiment, I can calculate that. If you look on the battery, it tells you the milliamp hours. What that means is this can supply 1 milliamp for 750 hours, 750 milliamps for 1 hour. At 1.5 volts, I'm drawing 150 milliamps. It should discharge in 5 hours. The AA battery should discharge in 16, the 9 volt battery in 3 hours. So I'm going to be collecting up to 16 hours of data. This is one of the reasons to use a text file. I don't really want to sit around for 16 hours collecting data. Well, the Pi Pico will do it all for me. Also, you can get a lot of data. If I record data every second for 16 hours, that's 57,000 data points. The Pi Pico only has 256K of RAM. So you can quickly use that up. Maybe saving data every second isn't necessary. Might save it every 10 seconds or 20 seconds. So the programs. The program to measure the energy in a battery, what it does is it actually measures it every second, saves the data every 60 seconds. Every second, it will measure the voltage. From the voltage, I can calculate the power. That's V squared over R, assumes a 10 ohm resistor. I can find the joules. The joules is the integral of watts. So take the old value, add 0.178 watts times 1 second, that updates it, and milliamp hours. If I know the volts, I know the ohms, I know the amps. Times 1,000 gives you milliamps. Divided by 3,600 is milliamp hours. This is just the integral of the milliamps per hour. In terms of the code listing, it's kind of an abbreviated code listing. Full code is on Bison Academy. I am going to use a timer interrupt to set the sampling rate to 1 second. I will keep running the experiment as long as the voltage is above 0.5. I'm going to call this when it's discharged. This part right here is your 1 second sampling rate. Wait for the interrupt to kick in. When it does, run the rest of the code. I then measure the voltage with the A to D, convert to milliamps, convert to milliamp hours, convert to watts, integrate to get joules, and then write everything to a file. So here's what that looks like. This is the battery test program. The name of the file that I'm going to be writing to is AA battery 5. When I run the program, it clears everybody out and then measures the voltage of a AA battery as it discharges across the 10 ohm resistor. So here you can see the voltage. If I do V squared over R, that's how many watts I'm outputting. Correcting the resistance, so it's a 10 ohm resistor. There's the volts, there's the watts. When I integrate watts, I get joules. Volts over ohms gives you milliamps. Integrate that, I get milliamp hours. So this is creating a file. This one's called AA battery 5. Let it run for a while. So you're like 45 seconds. I can then, when the voltage drops below 5 volts, they're just disconnected it. The program stops. When it stops, I can open from the Raspberry file. It's Raspberry Pi AA battery 5. This file right here. There's the data that I just collected. And again, it doesn't have a whole lot of data because I just ran it for 58 seconds. But as you ran it, I'd be getting more and more data. This part up here, when I open the file, I open it as a quote A, append. So it appends to the old file. And you get columns of data. What one of those files looks like, if I do open from Raspberry Pi, and the files aren't on my Pi Pico anymore because I ran out of memory, so I had to delete them. But anyway, if you took that file and plotted it, here's what the voltage looks like for a AAA battery. It runs for about 500 minutes. Voltage goes from about 1.4 down to about 0.7 volts and then just drops off. Once I've got the reading, voltage versus time, I know the milliamp hours of that battery. I know the joules in that battery. Well, if I just take a single measurement, I really don't know much. To find out what the statistics are for that battery, I need to collect at least 2 data points. Basically, a single measurement means nothing. If I have 2 or more data points, I can use the student t-test. With that, I can find the 90% confidence interval for the energy in the battery in milliamp hours and find out what's the probability this battery actually meets specs, meaning it has at least 750 milliamp hours in it. Well, from the data, I can find the mean, find the standard deviation, use your calculator, use MATLAB, something like that. What this tells you is, assuming the data has the normal distribution, the mean is the average, the standard deviation is to measure the spread. This is what the PDF looks like for AA batteries or AAA batteries based upon my data. If I want to find the 90% confidence interval, well, that's where you do a student t-test. If you go to StatTrack, I can do a student t-test and say I have a sample size of 3, meaning 2 degrees of freedom. I want to have 5% tails. They'll calculate the t-score, 2.92. What that tells you is the need to go left and right, 2.92 standard deviations to capture 90% of the area. Doing that says, based upon my data, these AAA batteries should have between 893 and 871 milliamp hours. I can do a single-sided t-test. Now the spec is the battery should have at least 750 milliamp hours. Well, what's the area to the left of 750? That's over here. To do that, I find the t-score. How far is 750 from the mean in terms of standard deviations? It is 34 standard deviations away. That's actually really, really far. In terms of probability, to convert that to a probability, I have a sample size of 3, meaning 2 degrees of freedom. The t-score is 34. The area of the tail is 0. It's actually not 0, it's off the scale. So it's less than 0.0005. Basically, the manufacturer is actually telling the truth. This is actually kind of surprising. My experience is most manufacturers are very generous in their claims. In this case, the people who make these rechargeable batteries are actually telling the truth. When they say it's got 750 milliamp hours, it really, really does. So I'm actually kind of impressed by the rechargeable batteries I got from Amazon. That's for AAA battery. Let's try AA battery. Like one of these guys. Well, doing the same thing, I'll let it discharge across the 10 ohm resistor. It's rated at 2400 milliamp hours. Running the experiment, it starts at about 1.5 volts, discharges, and then just falls off. This case actually took 1200 minutes. That's actually quite a long time. I'd let this run overnight, run for a day. Only took 2 data points in this case. For 2 batteries, it had 2596, 2623 milliamp hours, this many joules. I can tell you some statistics about it now. Given the data, I can find the mean, find the standard deviation. That tells me the PDF. The PDF for AA rechargeable batteries looks like this based upon my data. It's only sample size of 2, but it gives you some idea. With the sample size of 2, the t-score becomes 6.31. Again, when you have less and less data, I need to increase the spread because I don't really that certain about what's going on with only 2 data points. If I collected more data, I'd get better results, but this took like 20 hours to run, so I just got 2 data points. Just using 2 data points, I can find the t-score for 90% confidence interval, and this says I'm 90% certain that each of these batteries has between 2487 and 2732 milliamp hours. I can find out the probability that they meet specs. To do that, I find how far is 2400 from the mean in terms of standard deviations. That's your t-score. The t-score is 10.8, is 10.8 standard deviations away. From StatTrak, I can find the area. Again, it's 10.82. I've got a sample size of 2, meaning 1 degree of freedom. My t-score is 10.82. The corresponding probability, drum roll, is 2.9%. Finally, let's look at a rechargeable 9-volt battery. This is a different brand I got off of Amazon. It's rated at 600 milliamp hours. I'll let it discharge across a 47 ohm resistor because a 10 ohm resistor, V squared over R at 10 ohms is 8.1 watts. That gets pretty hot. 47 ohms, you're doing 2 watts, nearly 2 watt resistor. Repeat for 3 batteries, and here's what it looks like. The 10 volt or 9 volt battery drops down to 7.5 and then falls off the rail. 47 ohms is actually pretty low load. That's why it's not at 9 volts. The milliamp hours I measured are 402, 388, 393 in corresponding joules. Based upon that, I can tell you the confidence intervals. My 90% confidence interval is any given 9 volt battery of this brand has between 374 415 milliamp hours. The rated is 600 milliamp hours. This is a case where this battery brand is being a little bit generous in their claims. So that's kind of why I was impressed with the first ones. They're actually being honest. But anyway, that's something you can do with text files. With text files, I'm able to read text files and write text files. It's actually pretty easy in Python. When I read text files, I can use that to control a program, like play a tune. I can use it to pass data for data to plot. When I write to text files, I can use it to save data. For example, when I collected data from a battery, I collected data for 20 hours. After 20 hours, saving to a file. The next day, you can come back, open up that file, and analyze it. So that's text files using Python.